Hello everyone, welcome to the second lab section of this course, which is quantum transport. So I'm Gitanjali, I'm a PhD scholar from IIT Delhi, and I'm the TA for this course. In each lab session, we will go through the concept that has been covered during this week, and we'll try to solve few problems that is related to this concept, as well as some conceptual problem, as well as some numerical problems. And if time permits, we'll try to clarify some of the doubts you must have. So let's start our session. In this week, we basically see what are the different type of surface states that a some metal semiconductor junction that can have, and we saw what is the effect of the surface state on the band diagram in the junction, and also we saw what are the factors that affects the mobility of the charge carrier in the junction. So let us start. So if you look at the bulk region of a crystal, so the bulk inside the bulk there are periodic arrangement of atoms, ions, or any molecules in there. But inside the bulk, we can represent the wave function in terms of the Bloch wave function because there are periodic arrangements, so we can represent the wave function of the particle inside the bulk region in terms of the Bloch theorem. And that means this wave function will be oscillatory in the inside the bulk, and as it moves towards the surface, it will decay exponentially. So inside the bulk, it will be a Bloch function, but when we see what is happening at the surface, for surface, there is a breaking of symmetry there. So that is why the wave function we can't represent in terms of oscillator function. There, the wave function will be localized around the surface, and it will decay exponentially as we move away from the surface. So this is how the wave function will behave, and this is all due to the different types of potential that the charge carrier will experience while moving from one region to the other region. So if we represent the potential uh, inside the bulk, there is periodic arrangement. So let's say these are the lattice points where the basis atoms are there. So inside the bulk, because of the periodic arrangement, the potential experienced by this charge carriers will be somewhat like this. But when it reaches the surface, the potential will now become a kind of a barrier function. So because there is a breaking of asymmetry, so that is why the potential experienced by this charge carrier will be different from the potential that it will experience at the bulk region. This is the bulk and this is the surface region. Okay. So this surface state, if we want to find out where this surface state lies in the energy band diagram, and we found that if we look at the band diagram of a, let's say, semiconductor, so there is conduction band, there is valence band there for the bulk. This is for the bulk where the potential is same, and it's not on the surface. So, and we found out that this surface state will lie inside this forbidden band gap region. So they do not lie inside the allowed band state, like they don't fall in the conduction band or they don't fall in the valence band. So they always lies in the forbidden band gap region of this energy band diagram. Okay. And so that is why they will decay exponentially to the conduction band as well as to the valence band. Now, if you look at the different type of surface states, like depending on the charge carriers, depending on the kind of charge carrier that is there in the surface, we can have two types of surface states. One kind of surface state that we can have is acceptor-like surface states, and the other kind we have is the donor-like surface states. So if we look at the first one, so it says it's the like a acceptor-like surface states. That means it takes electron from the conduction band of the system. So this means this will takes electron from the conduction band. So that means this is one point, and so when it will take electron, it will get negatively charged after accepting the electron from the conduction band. And this will be these are will be neutral when it is empty. So in the initial state, when it is not accepting, it will be neutral, but after accepting the electron, it will become a negatively charged state. And if you want to represent this surface state in the EK diagram or the energy band diagram, so we have somewhat like this. This is valence band, this is conduction band, and the surface state will lie somewhere here, closer to the conduction band, where it can accept the electron. So this is acceptor-like surface state. Now for the donor-like surface state, so it is quite obvious from the definition. So it will donate the charge carrier. So it will donate electron to the valence band, and this will become positively charged after donating the electron. The third point that we can have will be this will be neutral when they are filled. And if you want to represent in terms of the EK diagram, then this is the conduction band, this is the valence band, and the donor-like states, this will lie somewhere here, closer to the valence band. This was accepted like. So this is the donor leg. So these are the two kinds of surface state that we can have depending on whether they are accepting the electron from the bulk or they are donating electron to the bulk. So there is always a transfer of charge when we talk about this donor or receptor like surface state. So this what is the consequences of this? So this will change the doping or carrier concentration of the system near the surface, because surface is where the system is accepting the electron and donating the electron. So that is where near the surface there will be a change in the doping concentration or the carrier concentration. So this will, because of this, the band diagram will now change, because now the charge carrier distribution is different at the surface from the bulk. So because of this, we'll see a bending of the bands in the near the surface. So if you now let's talk about the band bending for N type and P type. So let's say in brief what will happen to the bands near the surface because of this donor and acceptor like the surface states. So what will happen to the N type is because the N type will donate electron to the sorry, it will accept electron from the conduction band. So there will be a transfer of charge from the conduction band to the valence band. So let me plot it first. So these are the initial band that we have without any surface state. Now, when we are considering the surface state, what will happen? Some of the electron from the conduction band will move to the uh, acceptor-like states. So, because of this, now the energy of this region where the charge transfer is happening near the surface, they will bend upwards because there are now no charge carriers there. So the energy, so they will move away from this bulk level. So this will become like this. In the bulk, they will remain as it is, but in the surface, it will move upward for the N type. Similarly, because the now what will happen to the valence band? Because the bands is moving upward, because there is a transfer of charge from conduction band to the surface state. This the gap, which is the band gap, they will remain constant for a system. So that is why to maintain this band gap now, what what you can guess is this valence band will also move upward. Okay. So this will be the effect of surface states to the N-type semiconductor. Now for the P-type, the situation is totally opposite to the N-type one. So instead of donating the electron now from the conduction band to the surface state, now the surface state is closer to the valence band and it is donating the electron to the valence band. These are the conduction band. So because now these states are accepting electron, they will bend down. And to maintain the band gap between this conduction and valence band, the conduction band will also move downward. So in short, for N-type, whenever there is a effect of surface state, the bands near the surface will move upward for the N-type and it will move downward for the P-type one. So this is the effect of surface states on bands. Now to calculate what will be the distribution of the charge near the surface or what is the potential experienced by the charge carriers near the surface. So we can make use of Gauss law. So let us say there is a depletion region after the charge transfer. Let's say this is Z depletion. They may consist of positive ions or negative ions depending on the type of charge carriers. So let's say ND, it is the donor density. So we are now considering the N-type semiconductor. So that means this will be positively charged immobile ions. So donor density, we know for a particular type of semiconductor, we have a range of donor density. Like for N type or P type, it basically it ranges from 10 to the 16 to 10 to the 18 per centimeter cube. So from the donor density, we can calculate what is the surface electron density. If we take there is a complete ionization of the donuts when we combine two different types of material. So surface charge density, if we represent it in terms of Ns, this is nothing but Nd multiplied by the length of this depletion region. So that means we have the charge density rho is minus E and D. So surface electron density, this we can write it as Nd. So this we have already seen, and which is Ns, right? Now for the, if you recall the Gauss law of electrostatics, this is divergence of A is rho by epsilon naught. And for electrostatic case, we can write it as electric field is negative of gradient of V. So this will be del square V rho by epsilon naught. Or we in Cartesian one, we can write it as dv square d square V by dz square is rho by epsilon naught. Rho is minus E and D, E into donor density. And for a medium, we can write epsilon naught as a epsilon, which is nothing but epsilon naught into the relative permittivity. So if we oh, solve this equation, double differential equation, uh, we have B of Z is minus E and D epsilon naught epsilon R Z minus Z dip square. So this is a function of potential, function of Z. What is the variation of potential? If you want to find out the potential at the surface, we just let's say Z equal to 0 is the where we are considering it's the surface. So for Z equal to 0, this will be E and D epsilon naught epsilon R Z Z depletion region square. So this is how we can calculate what is the different potential that the electron will experience when it moves from the bulk to a surface. Okay. Now in the second case, what we have seen here, one thing we can notice that the potential is directly proportional to Z depth square, and it also directly proportional to what is the donor density. This relation you should remember so that you can uh, solve the problems that will be asked in the assignment. Okay. Okay. So now let us see what will happen when we apply a voltage. So because of this, because we here we can see that when we combine, let's say two different type of semiconductor or one metal with a semiconductor, so there will be a transfer of charge from one region to the another region, and there will be a region where immobile ions will be there, which is the depletion region. So the depletion region is kind of they kind of act like a insulating layer because they prevent the flow of charge from one side to the another side. So they create a built-in potential that will restrict any further flow of charge carriers. So this we can use this to avoid the use of oxide layer during the getting application. So oxide layer is kind of acting like a insulating layer for getting application, but because here there is already a depletion region is getting created, which prevent the flow of charge carriers. So we can avoid the use of oxide layer when we are combining two different metal. But it also depends on the kind of material that we can use. So it's not like we can combine any type of material with the other type. So it does have some condition to it. But because there is a creation of this depletion region, which is a non-conducting region, we can use it as a oxide layer for the gating application. So we have seen before the potential that the charge carriers will experience when it move to the surfaces. V of Z is minus E and D epsilon naught epsilon R Z square. So that means if you want to find out the potential energy, that is the total stopping potential, kind of a total energy that the electron will experience, which will prevent the flow of electron from one side to the another side. So this we can easily get it by just taking the potential and multiply with the charge carrier, the charge of the carrier, which is electron minus E. This is minus E Vz. And if you put it here, this will be E square and D Z square d epsilon naught epsilon R. And we can easily find out what is the length of this depletion region by using this relation. So this will be epsilon naught epsilon R phi B E square and D. So in terms of a voltage, we can modulate what will be the length of this depletion region. Like we can contract this length or we can expand this length. It depends on the kind of voltage we're applying to one of the region as respect to the other region, or it also depends on the electron affinity and the work function of this uh, two types of material that we are combining. So depending on this, we can also change this depletion region length, which in the presence of a getting voltage, we can write it as epsilon naught epsilon R phi B minus EVG by E square and D. So this is in the presence of a gate voltage. So now we'll see one of the example of a metal semiconductor junction and how they will operate in the presence of a getting in terms of a getting or a bias voltage. So let us consider the first case. So we'll take this semiconductor as a n-type semiconductor. And let us see the case where the work function of this metal, it is greater than the work function of this semiconductor. So we say it is a Schottky type. So let us draw the band diagram first. So phi m is greater than phi s. This is the vacuum level. Let's say this is the metal. This is the Fermi level of metal. And the difference between the from the Fermi level to the top of to the vacuum level, it is the work function phi m. For semiconductor, it's given phi m is it is greater than pi s. So let's say the Fermi level of this semiconductor is lying here. Semiconductor. This is phi s. The difference between vacuum level and the Fermi level. This is N type, so the EC will be closer to the Fermi level. And let's say EV is somewhere here. The difference between the vacuum level to the conduction band edge. So this is, we call it as a electron affinity. So that means we can write, so this is metal, this one is semiconductor. So we can write the phi s as the electron affinity of semiconductor plus this difference, which is EC minus the Fermi level. Okay. So this is before the contact, what will be the energy band diagram representation. But when we move this metal and semiconductor closer towards each other, so what will happen, because the work function of the semiconductor, it is less than the work function of the metal. So what will happen? The electrons that is present here, they will move to the metal part because the work function is smaller here. So they will move to the metal side, and because of this charge transfer, so what will happen after some time, there will be the the surface of the semiconductor, it will become positively charged because the electron is going to the metal side, and there will be a net negative charge on the metal side because the electron is coming from the semiconductor side. So because of this charge transfer, there will be a potential barrier. So electric field will be created in this direction, so which will ultimately create a built-in potential. So this built-in potential will prevent any further charge movement. Okay. And because of this built-in potential and the charge carrier movement, we will see, as we have seen before also, the bands will bend accordingly. Like for the N type, it will bend upward, and for the P type, it will bend downward. So if we represent it in the diagram, so this is the metal side. Let's say, always remember that whenever the system is in equilibrium without any bias voltage, it must have only one Fermi level. If we are applying a voltage, then it's possible to have two Fermi level, but in equilibrium, when there is no applied voltage, the system will only have one Fermi level, and we represent the bands according to this single Fermi level energy. So as I said, the bands will move upward for the n type. Similarly, the valence band, it will also move upward. And we'll see a built-in potential because of the space charge. So V0, we can write it as phi m minus phi s. And this built-in potential will prevent any further charge carrier movement from the semiconductor side to the metal side. Similarly, from the in the semiconductor side, we'll see a Schottky barrier potential, which will prevent the movement of electron from the metal side to the semiconductor side. This is phi b, Schottky potential. So this will be phi m minus chi m. And there will be a depletion region. This Z depth. Okay. So this is how the band will bend when we combine metal with a semiconductor. Now let us see what will happen when we apply a voltage. So if you recall, for the reverse bias case, we have two conditions. One is reverse bias, one is forward bias. For the reverse bias case, we apply negative voltage to the metal side and positive voltage to the semiconductor side. And because of this applied voltage, what will happen? The depletion length will decrease. So that is why the current will increase for this case. On the other hand, for the forward bias case, we apply negative voltage to the semiconductor side and positive voltage uh, to the metal side. For this case, the depletion length will increase, and this prevents the carrier movement, charge carrier movement. So that is why the current will be negligible for this case. So we'll see so this is for the reverse bias case, the current will be negligible. So for this case, when the work function of metal is greater than the work function of the semiconductor, we see a rectifying effect. So by rectifying, we mean that there will be only unidirectional flow of current. So there is no bidirectional current flow. Only in one direction the electron is allowed to flow. So that is why we say it's acting like a rectifier. On the other situation, like if the work function of this metal is less than the work function of the semiconductor, so for that case, what will happen? Uh, Let us first plot the diagram first. N-type semiconductor to a metal, but with the condition that phi m is less than phi s. This is the metal side. This is the Fermi level, and this is 5m. Let us say for the semiconductor, 5m is around Fermi energy level is EF here. Says 5s. So 5s is greater than 5m. So because this is n type, EC will be here, and there will be EV. Now for this case, because there is the work function of metal is less than the work function of semiconductor, so electron will flow from metal side to the semiconductor side. So there will be accumulation of electron in the semiconductor region. In this situation, the junction, it typically acts like a ohmic contact. So no matter what is the bias of this total system, it will also always have a ohmic like relationship with the voltage. So it acts like a ohmic contact. Okay. So this is about what will happen to the metal semiconductor junction. Now, what if we have a semiconductor to semiconductor junction? So that is for that case, we say this is a semiconductor heterostructure. So heterostructure, it means we are combining two different type of semiconductor. So to see, to quantitatively see what will be the bending, what will be the height of this bend. So for that case, we can you make use of Anderson's rule to find out what is the offset in the conduction band and what is the offset in the valence band. So this rule says to find out the conduction band offset, or the valence band offset that we see during combining two different types of material. First, what we need to do, we have to align the vacuum level to a single energy level for the two materials. So this is the vacuum level. Now we have to represent all the affinities and electron affinity or the work function of the materials on either side of this interface according to this vacuum level. And let's say we have a situation like this. We have a semiconductor like where the conduction band is here and the Fermi level for this is here. This is the valence bandage. So that means this will be the band gap energy for the first side, and the difference in vacuum to the conduction band is the electron affinity I1, and the difference from vacuum level to the Fermi level is work function. Similarly, for the second case, let's say we have electron affinity. The level is a bit, it's in the it's at a distance of, let's say, EC1 minus, this will be, the levels are getting lifted for this second case. This is not on the same level. So this is EC2, Fermi level is here. So that means this energy difference will be the work function. And let's say we have the valence band. This is EV2. Yeah, this is VG2. So first we need to align the vacuum level. Then we had, according to the vacuum level, we have to show the electron affinity, work function, and the band edges, conduction band and valence band edges according to that. After that, we can calculate the band offset. So the conduction band offset delta E C. This is because of the electron affinity. There is a band offset between the conduction band and the valence band, right? Because the electron affinity is it's the energy difference from vacuum level to the conduction band. So that is why the we can calculate the conduction band offset if we take into account the electron affinity difference. So this will be chi2 minus chi1. This is conduction band offset. Similarly, for the valence band offset, this we can calculate it as. So this is chi1 plus Eg1. This will give the location of the first valence band, and chi2 plus Ez2. It will give the location of the second valence band is. So that means we can find out the valence band offset if we take into account chi1 plus Eg1 for the first and take a difference it to chi2 plus Ez2. This we can write it as chi1 minus chi2 plus Eg1 minus Eg2. Or chi1 minus chi2, this is nothing but minus of conduction band offset plus the band gap difference. This is the valence band offset. In the plot, we can represent this offset as a like this we have seen before also. This is the conduction band offset and there will be a valence band offset. So depending on where the conduction band and the valence band of these two types of material is. So now we have calculated the conduction and valence band offset, right? So depending on where this conduction band and valence band of this material on either side of this interface is lying. So we can have three types of semiconductor heterostructure. So types of semiconductor heterostructures. So we have three types. Type 1 is straddling. Type 2 staggered. And type 3 it is broken or mismatch. So to identify which one is a type 1 type semiconductor heterostructure, which one is type 2 and which one is mismatch, we can see the relative position of conduction band and valence band on either side of this interface. So for type 1, the conduction and valence band of one type is lying completely in the completely within the region where the conduction band and the valence band of other type of material is there. So what I mean is, if we say the conduction band of one type is here. Then for the second type, it is completely lying in the region between this conduction and valence band. So this is the reason where the conduction and valence band of the other type of semiconductor is lying. So this is we say it is a type 1. For straggling, what will happen? One of this band will move out outside this region. So for that case, we say this is staggered. This is conduction band. This one is valence band. So one is here, other is here. So this we say this is a type 2 semiconductor heterostructure. For type 3, uh, neither of this conduction band and the valence band of the other type of semiconductor is lying within this region. So they will move outside this, they both will move outside this region. So in that case, we say this is a type 3 semiconductor heterostructure. We can also see the examples of this type 1, type 2. For type 1, let's say gallium arsenide and aluminum gallium arsenide, they form the type 1. For type 2, indium arsenide, gallium aluminum plate. And for type 3, we have so these are one of the example of type 1, type 2, and type 3. Afterwards, towards the ending of this week, we saw what is the expression for the mobility and what are the factors that will affect the mobility of this semiconductor and metal junction or the carriers. So let me just briefly go through it, then we'll start solving our numerical problems. So carrier mobility, if we recall, we can write J is NEVD, or this is also sigma E. Where sigma is N square tau by M E. So sigma, it is the conductivity and it is related to the mobility of the charge carriers. So that means from this two relation, we can say mobility is directly proportional to the scattering time. So depending on the scattering time, the mobility will get affected. So there are different type of scattering event that can have inside a complex semiconductor. So one is ionized impurity scattering. So this is because of the ionized donors or receptor or due to whenever we have a doping. So we'll have a ionized impurity scattering. Second case, we have phonon scattering because of the lattice vibration. And this is controlled by the temperature. Whenever we increase the temperature, there will be more lattice vibration and there will be more scattering. So that means the mobility will now decrease. Third type we have is piezoelectric scattering. So whenever there is a piezoelectric material is there, there will be a local electric field that will be created. And this will also leads to scattering. For fourth type is we have is surface roughness scattering, and this is due to a mismatch in the lattice at the surface. So because of this, so we will have a disorder in the surface, and this will affect the mobility. And the fifth type we have is the electron electron scatter. So depending on the scattering event, we will have different types of we will have different mobility. And for quantization, so whenever we are considering the quantum transport, we need to have high mobility. And this high mobility, this will leads to larger mean free path. So that means there will be less number of scattering event. And this ultimately leads to energy quantization. And as we have seen before also, for quantum diffusive, we need to have the device length. It should be greater than elastic mean free path or Fermi wavelength, but Le should be less than L5. On the other hand, for quantum ballistic, we need to have lambda f in the order of L, which is less than Le and L5. Okay. So let us we'll see other details in our labs in our next lab session. For now, let us start solving our uh, numerical problems that is related to week two concept. Okay. So in the last live section, we have left with few more problems. We'll try to solve it first, then we'll move forward to solving the next question for week two. Please go through the question once. So for this, let me read out the question first. So there is an experimental measurement of a 2D electron gas at 4.2 Kelvin shows a mobility mu of 10 to the 6 centimeter square per volt second. The effective mass m star is 0.067 me and the carrier concentration is 10 to the 12 per centimeter square. Calculate the mean free path and determine if it is a ballistic or diffusive for a device length of 5 micrometer. So first we need to calculate what is the mean free path. Then we need to determine for this mean free path what is the type of transport, whether it will be diffusive or whether it will be ballistic if the device length is 5 micrometer. I will give you some time to think about it and how to solve it. Then I will start uh, showing the solution. First, try to recall what is the expression for mean free path of a system, and try to relate. These are the given parameter. Then try to relate whether you can find out the mean free path if you're given mobility and star, and try to recall what is the uh, parameter that you need to find out using this information. So it's given it is a 2D electron gas. Temperature is also given, and mobility of the charge carrier is given, effective mass given, and the carrier concentration is given. So from this given information, you first need to calculate the mean free path, and if you relate the mean free path with the the device length, then you can find out whether it is ballistic or whether it is diffusing. So for 3D system, if you recall the mean free path, it is sorry, it's a wrong symbol. Mean free path is LF. So mean free path, you can write it as the scattering time multiplied with the velocity. So that means you need to find out what is the velocity and what is the scattering time. And if you recall scattering time, we can calculate it using this relation, using this given parameter, but we don't know what is the velocity, the Fermi velocity of the charge carrier. So for that case, we need the Fermi wave vector, and if you recall the relation between Fermi wave vector and the Fermi velocity, then it's possible to find out what is Vm. But first, we need to find out what is the Fermi wave vector for the 2D system. So for the 2D, for 3D, we have seen what is the relation. It is 3 pi square n power 1 by 3. Similarly, first we need to see what is the kf for the 2D system. So for 2D, we can write kx is nx pi by lx and ky is ny pi by ly. So that means k space volume of a single state in k space will be pi by lx pi by ly. So that means this is pi square by a for the single state. Now to find out what is the total number of states in a given small volume. So we need to first find out what is the total volume of the K space. So K space volume of a circle. So in 2D we can take a circle. In K space will be pi K square. So that means the total number of filled state in K space this will be N is a circle, maybe single state. So this is a circle, right? So this should be A because it's 2D one. multiplied by 2, which is the spin factor of the charge carrier, multiplied by half and half. So this is to take into account the positive states, because negative states are nothing but they are similar to the positive states. So there will be redundancy. So that is why we say we divide it by 1 by 4. So this will be by kf square and pi square a half. So that means now we have 2 pi n by a is kf square. So kf will be 2 pi, the carrier concentration for the 2D system, and 2 for half. So this is the kf, the Fermi wave vector for the 2D system. N is already given, so that means we can calculate what will be k. So for Vf, this will be h got kf by m star. So that means h got by m star root over of 2 pi n. Let us put the values. H got will be 1.054 to 10 to the minus 34 multiplied by 2, 3.14, and n is 10 to the 12 per centimeter square. We can convert it to meter square divided by m star. M star is 0.067 times Me, which is the mass of electron. This is 9.11 into 10 to the minus 31. So this will come out as 4.33 into 10 to the 5 meter per second. So we have calculated what will be the Fermi wave vector, Fermi velocity from the Fermi wave vector. Now what we need is the scattering time. So tau t is, this is mu m star pi e. This relation we already know. Mobility is given 10 to the first 6 and m star is 0.067 me. 10 to the 6 0.067, and okay, we need to convert it to meter square. To 6, right? 36 centimeters square, so this will be 100. 1.6 into 10 to the minus 90. So this will be 3.8 into 10 to the minus 11. So that means mean free path, this will be Vf time tau. So 3.88 10 to the minus 11, 4.33 10 to the 5. And this will be the value that we'll get is within 16.5 micrometer. Okay. So this is the mean free path of the charge carriers for this system. Now, to see whether the transport will be diffusive or whether it will be ballistic, we need to calculate. One thing we can do is we know KF, the Fermi wave vector, so we can calculate the Fermi wavelength, and we can compare the Fermi wavelength with the device length, and according to that, we can uh, see whether it is diffusive and whether it is ballistic. So lambda f will be 2 pi by kf, and kf is square root 2 pi n. So that means this is 2 pi by n. So 2, 3.14, and this will be 12, 12, right, per centimeter square. Oh, yes. And 12 minus 4. So this will be 2.5 to 10 to the minus 8 meter or 0.025 micrometer. This is the Fermi wavelength, and it's given the device length is 5 micrometer. Let us compare it to the Fermi wavelength. So device length, it's given L is 5 micrometer. So that means if we divide device length with Fermi wavelength, this will be 5 by 0.025, which is 200. So that means the device length is much greater than the Fermi wavelength. So, and if you see the chart, this lies in the diffusive transport section. So diffusive transport will dominate for this device if you have mobility or the carrier concentration given in the question. Okay, so in this way you can calculate. This is for the 2D. Similarly, you can do it for 1D case. For 1D case, first you need to calculate what is the K value. Then from that you can calculate what will be VF. And after calculating all, we need to just calculate what is the with if the question is asking about mean free path, you can go on to calculate mean free path. And to compare it, whether it is diffusive or ballistic, you need to compare whether it is whether the device length is greater than. So you need to compare the device length with the Fermi wavelength. Okay, so in this way you can decide whether the transport is diffusive or ballistic. Okay, so for second question, we have mean free path of gas molecule. It is at a constant temperature, mean free path increases with increasing the pressure, or at constant pressure, the mean free path decreases with increasing the temperature, or lambda increases on decreasing the size of molecule, or lambda increases as the number of molecules increases. So which one of these following will be correct according to the mean free path of the gas molecule? So mean free path is nothing but the distance traveled by the molecule between two successive collision, right? So you need to check which one of these factor will affect it. So for a gas molecule, we can write mean free path is 1 by root 2 pi d square n prime. So d is the molecular diameter. One minute. D is the molecular diameter and n prime is the number density, which is this is the number density. So that means if you increase the uh, number of molecules, lambda will increase. Lambda will decrease. So this is not correct. So if you decrease, lambda will decrease the size of molecule. So this says if you decrease it, then lambda will increase. So that means the correct option is option C. Remember this relation. Okay. Question number 16, it's based on the Drude model. It says which of the following is true for the Drude model. First option is whether the particle follows Maxwell-Boltzmann statistics for this Drude model, or is for the second option we have is the applied field strength increases, the current density also increases. Option C, conductivity of metal is directly related to the mean collision time, or option D is all of the above. Which one of these you think is the correct option? So we can easily see that all of these option are following according to the Drude model. The particle does follow the Maxwell-Boltzmann, and as we apply the field strength, the current density also increases. J is sigma E, and the conductivity of the metal is tightly related to the mean collision time, which is sigma is n square tau by m. So that means option D will be the correct option. Question number 17, we have suppose the temperature of a system is increased to TF equal to, temperature T equal to 400 Kelvin. This T, right? P. Then what is the range of energy around the Fermi energy level which contribute to the transport of charge carriers, and how will this range get affected when the temperature is increased to T2 equal to 600 Kelvin? So we are given two conditions. One is temperature, it is at 400 Kelvin for this case. What is the energy range around this Fermi level which contributes to the transport of charge carrier? And when the temperature get increased to 600 Kelvin, how this delta will get affected if you increase the temperature? So if you recall the Fermi Dirac statistics, it gives the what is the probability that the charge carrier will be occupied in a given energy level. And this probability is given by Fermi Dirac statistics, which is 1 by 1 plus e to power E minus EF by KBT. So this gives the probability that a particular state will be occupied by electrode. And if you plot this Fermi-Dirac function, so for temperature T equal to 0, all the state up to Fermi level will be occupied, and all the state after the Fermi level will be empty. This is equal to A. This is as temperature 0 Kelvin. Now, when we increase the temperature, what will happen? All the states that is closer to the Fermi level, they will start moving to the next higher energy level. And as we increase the temperature further, more and more electron will try to occupy the higher energy states. This is T2. Let's say this, we say this is T1. This is T2. And T1 is less than T2. And the energy spread around this Fermi energy level, that so the only these states that is closer to the Fermi energy level, that is getting occupied by the next high energy level closer to this Fermi energy level, they will only correspond to the transport. And this length, this energy spread, this has been calculated as, this has been verified, and it is this value will be delta is around 4 kBt. So this energy spread is 4 kBt. So that means the energy spread does depend on the temperature, and as we increase the temperature, the energy spread will also increase. So to calculate, so we are given two temperature, one is 400 Kelvin. So for the first one, the energy spread will be delta is 4 kBt. Kb is 1.38 into 10 to the power 23 times 400. So this will be 2.208 10 to the power minus 20 joule. Or in terms of electron volt, we can just divide this by 1.6 into 10 to the power minus 19. So this will come out as 0.138 electron volt. This will be only the particle within this range around this Fermi level will participate in during the transport. Now, when we increase it further, T2 is 600 Kelvin. Delta E will also increase. So delta E2, and we see that it is slightly progress low temperature. So that means delta E2 is delta E1 T2 by T1. T2 is 600, T1 is 400, 654 and 0.13. So this will be coming as 0.207 electron volt. Okay. So in this way, you can calculate if it is given, it is following the Fermi-Dirac statistics. You can calculate what is the range of energy within which the electron can participate during the transport. Okay. Question number 18. It's given a semiconductor is transparent to light with a wavelength longer than 0.87. What is the band gap energy for this case? Let me give you some time. Please go through the parameter and calculate what will be the band gap energy. So this question is quite easier one. You are given it is transparent to light with a wavelength longer than zero point 0.7. So that means transparent, it is allowing the wavelength to pass through the semiconductor. So that means all the wavelength below the 0.87 it will be blocked. So this wavelength will now wavelength that is below 0.87 they will correspond to the band gap energy. So Eg now will be uh, Sc by lambda H is 6.625 10 to power minus 34. C is 3 into 10 to the power 8 and lambda is 0.87. So this will be 1.42 electron. Question number 19, it's given suppose P1 represents the probability that a state is occupied delta E above the Fermi level and P2 represents the probability that a state is empty delta E below the Fermi level. Then which of these following correctly represent the relation between them? Whether P1 and P2 they are equal, the probability is equal, whether P1 is greater than P2 or whether P1 is less than P2 or it cannot be determined. Which one of this will be a correct relation between P1 and P2? So P1 represents the probability that a state will be occupied delta E above the Fermi. So that means we can write P1 is 1 by 1 plus e to power E minus EF by kBT. And E minus EF it's given it is delta I. The state is delta I above the Fermi level. That means the difference is delta I. So this will be 1 plus e to power delta E by kBT. And P2, it is the probability that a state is empty delta E below the Fermi level. So probability of empty state is 1 minus probability of occupying that state. So it were E2 minus EF by kBT. E2 minus EF, it's let's first simplify it further. So this will give it for E2 minus EF by kBT 1 plus e to power E2 minus EF by kBT. So this will simplify to 1 by 1 plus e to power EF minus E2 by kBT. And EF minus E2, it's given the state is delta E below the Fermi level. So this will be 1 by 1 plus e to power delta E by kBT. So that means P1 is equal to P2. So if the states are equally separated from the Fermi level, then the probability that the state will occupy delta E above the Fermi level, it is equal to the probability that the state will be empty delta E below the Fermi level. So P1 is equal to P2. Okay, so let us move to our next problem. It's a conceptual one. It says which of these following statement best describes the physical origin of the band bending at a uh, clean metal n-type semiconductor interface in equilibrium. So option is whether it is due to mechanical strain at the interface which alters the lattice constant of semiconductor, and B is difference in carrier mobility between the metal and semiconductor leads to band bending. C is band bending occurs when external voltage is applied across the contact and it is absent at zero bias voltage. Option D is it is caused by charge transfer between the metal and semiconductor to align the Fermi level, which leads to space charge in semiconductor. So, which one of these is correctly describes the physical origin of band bonding at the metal and N-type semiconductor junction? So, if we look at the options, we see that option D is the correct one for this case, because whenever we combine metal with N-type semiconductor, they have different work function and they have different Fermi level. They don't line up when we combine them. So when we combine a metal with a N-type semiconductor, what will happen depending on the work function, electron will flow from one side to the other side. And because of this electron flow, there will be accumulation of charge on one side, maybe positively charged or negatively charged on other side. And this charge, they will now create a local electric field, or what we say the built-in potential. And this built-in potential, because of this built-in potential, the electrons at the surface or at the interface, they will experience different kind of potential. And so because of this, now the band will bend. So the whole point of band bending, it occurs because these two types of material, they have different type of work function, different Fermi energy level. So when we try to combine them, they try to in equilibrium, they try to align the Fermi energy level to a single level, and due to the charge transport, we'll see band bending. Okay, so correct option will be option D. The second question, it's given in the context of band diagram. What does band bending near the surface of an N-type semiconductor signify? Whether it is signified by the accumulation of electrons near the surface relative to the bulk, or a transition from N-type to P-type doping at the surface, or a uniform distribution of charge with no built-in electric field, or it signifies a depletion of electron near the surface, leaving behind ionized donuts and creating a positive space charge region. This is quite easy because for N-type, they have more number of donor, so they can donate electrons. So electron try to transfer from one N-type to the other side of this material or the interface. So because of this electron transfer, ionized positively charged ions will be there in the N-type, and they will create a depletion region. So the correct option for this is option D. Question number third, it says which statement about the bulk versus the surface electronic wave function is correct? Option A, surface states are oscillatory in the crystal, while bulk states decay exponentially into the vacuum. Option D is bulk states are oscillatory throughout the crystal, but they decay exponentially as the surface is approached, and surface states decay exponentially into the crystal. Option C is both decay exponentially into the crystal with same decay length, and option D is none of these above statement are correct. Which one of the following you think is the correct option? So, if you recall, the bulk states inside the bulk there is periodic arrangement of atoms and ions. So, they will satisfy the Bloch's theorem. So, that means the wave function will be periodic. So, it will be oscillatory inside the bulk. But because of the breaking of symmetry at the interface, they will decay exponentially when they approach the interface. But for the surface states, there is no symmetry. There is a broken symmetry at the surface. So that means they are localized states. So they will be wave function will be maximum at the surface, and they will decay exponentially when we move away from the surface. So this we have also seen during the lectures. So if we plot the wave function, the bulk state, this will be oscillatory. But when you approach the interface, it will be decayed. This is the bulk region. This is interface. This is for the bulk state. Mhm. And for the surface states, the wave function, they will decay exponentially inside the bulk. But as it move to the surface, it will be maximum. But as we move away, it will also decay. So that means the correct option will be uh, this one, option B. Question number 4, it says which statement based distinguishes an ideal Schottky rectifying contact from an ideal ohmic contact on an N-type semiconductor. Option A, only ohmic contact requires a metal semiconductor interface. Schottky contacts don't, which is not correct. Option B is Schottky contact supports high bidirectional current with no barrier, which is also not correct. It supports unidirectional. While an ohmic contact blocks current in one direction, which is totally incorrect. This is not correct. Option C is Schottky contact creates a rectifying barrier for majority carriers, while an ohmic contact provides nearly barrier-free majority carrier transport, which is correct because Schottky, it's like unidirectional, so it's also a rectifying barrier. Option D, both Schottky and ohmic create always block minority carriers, but pass majority carrier equally well, which is not correct because Schottky it supports unidirectional. So the correct option is option C. Uh, Question number 5. Consider a n-type semiconductor forming a Schottky contact with a metal, which which change most directly promotes ohmic behavior instead of a rectifying behavior at the interface. Options are option A, choosing a metal with a much larger wave function than the semiconductor electron affinity. So that means phi m is much greater than electron affinity of semiconductor. Option B is reducing doping near the surface to make the depletion region wider. This also doesn't seem correct. Option C, heavily increasing the n-type doping near the surface. None of the above. So if you see it for the to promote the omic behavior, we need heavy doping because this heavy doping will decrease the depletion length and this will promote the omic behavior. So answer will be option C. Question 6, it's a numerical problem. In a n-type gallium arsenide semiconductor, calculate the donor density for a surface electron density of 1.8 into 10 to the 12 per centimeter square under no applied voltage. Consider complete ionization of donuts for their case. So go through the question. I will give you some minutes to solve it first, then I will go through the solution. So if you recall, whenever we have complete ionization of donuts and there is no applied voltage, so we can write the surface electron density is donor density, which is Nd, multiplied by the depletion length. So that means we can easily find out the donor density as surface electron density divided by the depletion length. Surface electron density is given, it is 1.8 into 10 to the 12 centimeters square. But depletion region length, if we recall the lecture, for no bias voltage, the depletion length of n-type gallium arsenide, you can take it as 60 nanometer. So if you put it and solve it, this will come out as 3 into 10 power 17 per centimeter cube. In the second question, it's a follow-up question for question number 6. So it asks, what is the Schottky barrier height for the above case? So you are given the donor density, surface electron density, and the depletion rate. You need to find out what is the Schottky barrier height. And if you recall, Z depletion, you can write it as epsilon naught, epsilon r, phi b, which is the Schottky barrier height, minus EVG. EVG is 0 because there is no applied voltage, divided by E square and D. So that means we can write phi d is E square and D Z depletion by epsilon R. All these parameter we know. For gallium arsenide, we take epsilon R is 12 and D is calculated. Z depletion is also we know. So phi B will be in terms of electron volt, we can write it as E and D, Z depletion, epsilon naught, epsilon R. So E is 1.6 into 10 to the minus 19. Donor density, it's 3 into 10 to the 17 per centimeter cube. This will become 23 per meter cube, and Z deb is 60 nanometer. So there will be a square. Yes. And epsilon is 8.854 into 10 to the minus 12, and epsilon is 12. So this will give a value of 1.6 electron volt. So the closest answer to this question is option B. Okay, from question 8 onwards, we'll try to solve in our next live session. We'll stop for today. So in this live session, we basically cover a few problems that is related to week 2 contents, and we also try to solve the numerical related to it. We'll meet on next Friday from the same time from 6 to 8 to solve our remaining problem as well as to see what is the concept that has been covered in week 3 and to try to solve a few of the question related to week 3 content. So we'll stop for today. Bye everyone.